Hello, my name is Gavin Oshock. I'm a senior from Hopkins, Minnesota, and my project is titled The Efficiency and Testing of a Fully Submersible Geared Water Turbine. My hypothesis was that the power output of a fully submersed water turbine with proportionally articulating fins would be greater than the power output of a traditional partially submersed water wheel turbine with fixed fins of equal size. The design I came up with rotates flat fins around an axis and changes their pitch to have the most drag at the top of a cycle and the least at the bottom. To decide what angle the fins of the turbine should be angled at in between the top and the bottom, I mathematically tested a range of fin angles at different positions around the turbine and looked for the angles that gave the maximum positive torque. I plotted these optimum fin angles during one cycle of a turbine. I was shocked by the emergent relationship that I found. As it turns out, there is a linear relationship between the ideal fin angle and the angle of the whole turbine with a slope of 1/2. To test my hypothesis, I built a scale model of the new design and a traditional design as a control. To test my turbines, I went to the 20-inch water flume at the University of Minnesota St. Anthony Falls Laboratory. I chained a motor to each turbine to measure the power output, and by attaching a range of resistive loads and measuring the voltages, I was able to record the electrical power. Here, you can see the new turbine in the flume. As you can see, the turbine is able to operate very well, completely submersed in water flow. At both water speeds, the new turbine in blue produced a greater power at all resistances. This strongly supports my hypothesis. All in all, after thorough physical calculations and building a working model, I was able to produce a design that systematically optimized the drag of a turbine to maximize torque. In addition, this same concept has the potential to be applied to wind energy harvesting with the possibility of incorporated solar panels, and layered hydro turbines, which take advantage of the submersibility to capture energy in a greater area and depth of water in the ocean. This same design could also capture tidal energy because the turbine is symmetrical and can capture flow energy in both directions.